So good morning. This is a wonderful December morning, one of the bright, shiny days that we actually get to see how our solar system works. We have PV panels on this utility cottage, and these are enough to power the whole building, but they're enough to power the construction activity of the Sustainable Living Center. The power comes from either the photovoltaic panels on the roof, or they come from the wind turbine. They come in here and they're stored in the batteries, and that's DC power, direct current, as in your car. And then it's converted by these inverters to alternating current that we can use in the building, like we typically use in our houses and our commercial buildings. So what you see in the building now is the scratch coat and the base coat of our stucco, and we have it tented so we can deal in the cold weather, and the top coat will go on next, and you'll have the finished look of the building. So now what we're doing is we're entering our job site, and you can see our sign here identifies the building, the authorized workers, and it gives the protocols of a natural building. And this is very important. We don't let anything through this gate that hasn't met our standards and our specifications, and it's very important to do that. And then what we have here is a list of some of the subcontractors that are working on the building that have embraced those standards that we have and are making sure that that goes into this building. What we have going on here is the earth blocks going up, and we're finishing the interior walls. We're going right up to the roof deck in some places and underneath the trusses here. So we had a machine here, and we made 26,000 of these, and most of them came from the earth right across the street. And what that block does is hold thermal mass. So it has the property of thermal mass. So when we're in the winter and we're heating the building, it holds that heat. In the summer when we're cooling the building, it holds that cool. So we have outside our exterior wall, underneath that stucco you saw going up, is a stud wall. So it's a 2x8 stud wall with cellulose insulation. Then there's a 2-inch gap, and then this earth block. And then that earth block and all the interior walls, except where we have bathrooms, that kind of thing, where you expect a lot of water, are made of these earth blocks. And what we do at night in the summer is we open up this clear store area that you see here. Automatically the windows open up at night, and it's called night flushing. So the hot air goes out this chimney effect, and we have a well in this corner of the building, but a 3-foot well outside, and an 18-inch pipe runs under and with diffusers. And so that brings the cool night air in, which resets the cool of this. And the exact opposite happens in this time of year, where we've got cold outside, and we've brought heat inside. And when we go up on the roof, I'll show you how the heat comes from our solar thermal panels. So then that heat is stored. It's like a brick oven. You fire up a brick oven, you build a fire in it for an hour, and it'll cook for 12 hours. The same thing here. Once we get the heat here, this earth here will store it. So we're up here on the roof now, and this forms several functions, this roof, aside from keeping water from getting into the building. This roof, if you look at it, looks like a little wading pool right now, and it kind of is. So all the water that hits this roof runs down this gradual slope, and this is a TPO membrane that is designed to keep the water out, but also it is reflective for these solar thermal panels. And I'll take you around and I'll show you how these work. So these are the solar thermal tubes, and they were made in Michigan, and what they are is a carbon fiber tube with a vacuum, and then inside it's a copper tube that is painted black or coated black with a conductive fluid inside. So as I said, the heat from the sun comes and hits this, and that tube heats up in the conductive fluid, and at the very end is a little copper lead that comes out, maybe as small as my little finger, maybe a little smaller. And each one of these tubes has one. And in this black box along the top, what happens is water circulates, comes in one side and then down the other. And as the water circulates, it passes these little copper leads. And it's like the coil or the heating element in our, say, our teapot or a kettle. And it provides heat. So in a sunny day like this, that lead will be about 350 degrees. And the water passing across there will produce temperatures in 160 to 180 degree range. And we have a 5,000 gallon tank inside the building to store this. And out here you'll see these drains. So the water drains and it goes down. There's 3 drains on this side and the other side. And we catch the rain, and there's going to be a 6,500 gallon cistern in the ground. And the water that we catch off the roof will be used in the building. It will be purified, filtered, and ultimately go through a ultraviolet ray, again like the sun. The ultraviolet ray, that's what a little electric instrument will produce it, and it will kill all the bacteria in it, so we can actually drink that water. And I wanted to spend a minute and talk about our windows here. This is windows by Serious Materials, and they have a number of interesting properties. They're what's called a heat mirror. So there's a suspended film in here that actually reflects out solar radiance where we don't want it. The windows are solar tuned. So in the south, where we don't want to get solar gain, we have a good heat mirror in there to reflect it back. In areas like our greenhouse where we want to get solar gain, it lets most of the radiance in. And these windows are highly insulated. A fixed window of this kind will have about R15 total, like R19 in the center of the window, and the entire assembly be up to R15 is a possibility. Now that is a stark contrast between your normal conventional windows. Typical windows are R3, you know, and they're gaping holes in your envelope. If you have, in our case, we have about R60 in the ceiling here, and we have about R35, 36 in the walls, and even R26 underneath our slab. So we aren't letting heat and cold coming in from the outside. But if your windows are just, and doors are just huge holes where that energy pours out, you're kind of wasting that. And Serious Materials is one of our sponsors, and we basically searched and we found what we felt were the best windows for our application, and they were the company that provided them, and we're very happy to have these windows. Now on the roof here, you will see this roof is just got a basic temporary membrane up there to cover the wood sheathing. Now what we'll go over here is a proper membrane and some shingles, and on this whole south side there will be solar panels like on the utility cottage. We have 2.6 kW on the roof of the utility cottage. We'll have almost 8 up here to give us about total of 10 kW in photovoltaic electrics. And our total building requirement is about 20, so we'll get the other 10 from our wind turbine. And on this little hip roof, we're hoping to put on integrated PV shingles. So they're shingles that actually have photovoltaics in them, and they go down like regular shingles. You nail them on. And then we're going to try to get some thin film on the utility cottage, and there's a standing seam metal roof, and there's 2 valleys between 2 seams that we can put that. So we'll be able to demonstrate for all the students and the visitors and everybody that comes to learn about this building all the technologies in terms of photovoltaics that are pretty much out there. Thin film technology, the panels, and the integrated shingles. And these are the areas now, what stage we're in this building is we've got the shell up, we're starting to finish that shell. Inside we've got the walls up, and we're just going to start finishing those walls. And we have all the rough-in for all of our systems. So the expense that's involved in these systems is what we're going to incur next. And this is what we're in the process of funding for, to take this building and make this building totally self-sufficient using renewable energy systems. We have the solar tubes on the roof that we saw, and they come down in here, and they come into this tank here. We have a 5,000 gallon tank that stores the water. And we've had cloudy days, cold days for quite a number of days, and our tank is down to 111 degrees. And right now our collectors are bringing heat in about 146 degrees, and that's going up every moment, 147 now, and 148. So what's happening is we've stored that water for a period of time. It was still over 110, which is what they temperature we want to circulate, and these pumps just came on. And what will happen is each of these pumps represents a zone, and it will pump the water through our radiant heating system, and I can show you these zones. Here's the manifold, and there will be tubes that come off here that will be underneath the floor that will provide the radiant heat. So from each one of these it'll come out and loop back and then go back into that tank. And the tank has coils in it. So the pumps come on, they circulate the water through there, pull the heat from that tank, and then bring that warm water through here and provide the radiant heat for the floor for the building. This thin pipe that's running along here, and then you see another one starting there and running along there, those are the 3 drains from our rain catchment in the roof of the building. And then they all go out and come out that corner of the building there into the cistern. Now these larger ducts, and then you come down to a smaller ducts, this is for our interior air quality. It's a recirculating system. And what that does is bring in fresh, clean air from the outside and circulate it in the building, so we have natural fresh air at all times. The other thing that that does in the summer is we don't just use the heating of the building from the solar panels. We actually are using the cooling from the heat of the sun. And that sounds a little counterintuitive. What we're doing in this building is pulling the humidity out. That's what's called the latent cooling. And if we take the humidity out from the air, it becomes very, very comfortable. So the way that we're doing that is, if you got some instrumentations, like say you got a new cell phone or a digital camera, that would have come with a little bag of crystals. And those crystals are desiccants, and what they do is absorb humidity from the air. So we have a liquid desiccant system that will be going in as part of our cooling system. And what that'll do is pull the moisture out of the air. The other aspect of our cooling is we're using the same tubes that we're using for heating. In the summer, we'll have cool water coming from the ground through a geothermal loop, and we'll circulate cool water through the floor. This is the air handler, and what it does is it moves the air for the recirculating system. And it's actually quite efficient. It has what's called a soft start, so what happens is it doesn't grab all its power needed to run its motor to turn the little fan that pushes the air around right away. It gradually ramps up. And that's important in an energy efficient building, that you have to design for your peak loads. So if you can reduce those loads, then you can reduce the size of your whole system. This building will be more than, it'll be carbon positive. We'll produce more energy than we actually use. And we're doing it with 2010 state-of-the-shelf technology that's available here. So anybody can do it. And the goal of this building, not only to provide a platform for students to learn and for professors to do research and teach, but is to influence the built environment. So we have an example here that anybody can come and see the systems and how they work and how they operate, and can use that in their own building projects in this region and elsewhere. So what we need now is to actually do the last bit of the building, which where all these expensive systems, these renewable energy systems, are incorporated into the building. So we need about $450,000 in cash, another $250,000 from foundations, and about $200,000 from industry sponsors. And that will allow us to complete the building, to set really a worldwide standard of how buildings should be built, operated, and maintained as a part of sustainable living on this planet.